Okay, in chapter 2, we talk about the atmosphere, something about its structure, maybe something about how it may have worked, what was the origin of it, and all. Just giving you a general overview of looking at the atmosphere as a whole here. Nothing fancy. So, what is the composition and structure of the atmosphere? We're going to just take a little peek at one thing. We think about the atmosphere, and it's all interrelated. Everywhere in the world impacts our atmosphere. Here in the United States, we impact other areas impact us. So the atmosphere isn't just made up of gases, it has particles in it, it has bacteria in it, it has all kinds of things in it. And one feature of our atmosphere that's kind of interesting when we're dealing in hurricane season right now is African windborne dust that hits us. It's called a Saharan air layer. It's dust that's transported, and you can see it on the satellite image here, and another view of it here. It comes in from Africa, and it can impact hurricanes. It actually decreases them. But you actually get it across the tropics. Sometimes it's even got into the east coast of the United States. The other year, visibilities in Miami went down to a half a mile because of Saharan air dust. And this actually contains within it disease-carrying organisms, and they can harm coral reefs and even impact algae blooms. So you can see this dust has quite an impact. So, looking at the atmosphere as a whole, we've all talked about memorable weather events. Guess what? Every one of you has been impacted by weather of some day. And many times it's maybe even different times during the day. The weather may impact what you're doing or how you're living your life. And you can see that weather can go from tranquil to nothing to very severe. We talked about that. So, what is the atmosphere? Well, the atmosphere is just one part of the Earth system. The Earth system consists of the hydrosphere, which is basically oceans, lakes, water, the geosphere, which is land masses, volcanoes, those types of things, biosphere, plants, animals, and then the atmosphere, which is probably the teeny tiniest, most thing of all of them, is a relatively thin layer of gases that's suspended above the Earth, and it has particles in it. And guess what? If you were to walk 18,000 feet, about 3 miles or so, you would actually reach half the way up through the atmosphere. And 99% of the atmosphere is below 20 miles. So think about that. As you're driving along, you travel 20 miles, you've covered the atmosphere depth. Pretty small. Currently, the atmosphere is mostly made up of nitrogen, which is an inert gas, and oxygen, which is the other one. However, there are other components. Argon is one, CO2 is one. There are other gases that impact our atmosphere as well. I was out west this last summer, and oxygen maintains its ratio throughout the whole atmosphere. In other words, if you're at sea level, oxygen at sea level is 20.95%. As you go higher up, oxygen is still the same percentage. However, at sea level, there are a lot more particles, air molecules there. They're compressed down in the lower levels. So as you go up higher, there are less air particles. And that means that, for example, when I went to Rocky Mountain National Park this summer, and I went above 12,000 feet, I had a lot of trouble breathing because there was significantly less amount of oxygen in the atmosphere. And there are also aerosols in the atmosphere all over the place. If you look at it, when you have a forest fire that puts debris in the air, wind. Back in the 1930s when they had the Dust Bowl in all times, industry can actually add things to the atmosphere. And none of that necessarily may all be, some of it may be very bad. Volcanoes. Water vapor can make up a significant part of the lower atmosphere, 40% sometimes in the lowest 1 kilometer. Without it, we wouldn't have the clouds and precipitation, which are necessary. CO2 for photosynthesis and for plant growth. So there's some good things about CO2. There are also some bad things about CO2 we're going to learn about. Pollution from man. When I was growing up, actually even in the early 70s, when I was in West Virginia and went through Kanawha Valley when I moved there, there was a ton of pollution. It's gotten significantly better since then. I used to go through Pittsburgh. Again, there was nothing but smoke all the time, it seemed like, and now we have really cleaned up our act a lot. It's much better. The scientific method is what's used in all science. We need to know just a little bit about it. So I want to use an observation case here. A question that was raised. I worked a lot on the east side of the Appalachian Mountains. And one of the questions always was, well, why so many times do thunderstorms die when they're coming across the Appalachians? Every once in a while, however, they come right on across and actually intensify. So what was causing that? What was unique to those times? So we took a bunch of observations. I was working with North Carolina State University at the time, and we discovered there was some stability in the atmosphere, which is a term we're going to talk about a lot later. And depending on how that was, we developed the hypothesis that maybe the certain parameter we were developing might explain some of that. So we would run that parameter, we'd look at it and see how it did in past cases with these thunderstorms moving across the Appalachians. We had to make some tweaks to it and stuff, but eventually we were able to draw some conclusions and then report those results and actually showed that, yes, we can predict with much more certainty when thunderstorms are going to continue to intensify and when they might not. It made a significant improvement in forecasting on this side of the mountains. Different models simulating like tornadoes here, numerical models. Guess what? You're not going to deal with a lot of equations in this course. There'll be a few, I can't tell you not, but there will not be a lot of math in this course. We got to observe the weather in order to understand it. So we have ASOS, which is at every airport in the country. Why is ASOS there? Because it's literally giving an observation every minute, so that continuously it can monitor the weather and it can broadcast out these observations to aircraft. Aircraft need these to be able to land correctly at an airport. They want to know what the weather is at that airport, especially if they're not even there yet. But this allows them to land and take off with much more confidence. There are other observing systems. There's a cooperative observer network. Every county in the United States has one of these little observation systems. They give literally, they're used for climate mostly, but they can also be helpful because they can give you a daily maximum temperature, minimum temperature, and maybe how much precipitation. If you look at the drought across the western U.S., these climate observing stations are part of what goes into estimating how bad that drought is. There's a community rain, hail, and snow network. It's volunteers. Hey, you're welcome to volunteer. All they ask is that you measure all kind of precipitation types. It's another way of filling in gaps. We don't see the weather everywhere in the United States. There just aren't enough observations. For example, if you were to ask me what the weather is in between Parkersburg and Charleston, West Virginia, there's no observation site there. I can guesstimate by looking at what's at one site and what's at another one, but I cannot tell you exactly what it is in that area. This is where cooperative networks like this, volunteers and all, help to fill in the gaps. Radiosondes launched every day, at least twice a day, around the world. These are upper air balloons that go up and eventually burst because the pressure at the surface is much greater on that balloon, and as it gets further up into the atmosphere, the balloon expands to where it can't go anymore, and it finally breaks. These are the instruments that are used. The dropsonde is exactly the same as a radiosonde, except it's dropped down. The radiosonde goes up with the balloon. The dropsonde is dropped from an aircraft, particularly over the water in the oceans, and especially in hurricanes. It gives you an idea of the observations of temperature, how much moisture is in the air, the wind, the pressure at a certain level. This pressure is going to vary as you go through things. Radar, wonderful tool for picking out precipitation. It can also tell you winds. It provides a lot of feedback to what's going on in the weather. And this is actual temperature profile averaged over what it looks like. And you can see the troposphere, which is where almost all the weather occurs. Temperatures generally cool with height. Now, when you get to the stratosphere, temperatures begin to warm with height. And we have the ionosphere, which is an area that impacted by the solar wind and actually can produce auroras. And you can see here there's some charts of auroras that people have taken. So let's just take a look here at just a couple things I wanted to show. This is the actual current map of where they expect auroras to develop in the next couple of days. And you can actually see there's not a high probability anywhere. But if you lived in the north, look at this coming across at night during parts of Greenland there. Oh yeah, here's parts coming into northern part of Canada and stuff. So you can actually see they're predicted by the Space Weather Center. I wanted to also show you a little look at soundings. I talked about radio sound data. Here is every location around the United States that takes an upper air observation. Well, guess what? Look at West Virginia. You don't have any. Or look at Ohio. There's only one in Ohio. It's out by Cincinnati. So there's not a lot. They're spaced out. But they help fill in gaps. And with that, I wanted to just give you an idea that this is an upper air sounding different than what I showed you earlier with the Stuvie. This is a skew T. And the only reason it's called a skew T is the temperature curve goes to the right at a skewed 45-degree angle. There's a reason for this for mathematical circumstances, but that is the only difference. So when you plot temperature, which is in red, green is dew point for the moisture. You just see if they still cool with height, and you can see how much dry air is in this case in here. Or you can look over here and see the winds and see as they change with height. Finally, I wanted to show you a radar map. This radar is down at Baton Rouge, Louisiana. They've had a lot of rain down in that area in the last few days. So here you can see all the rain that's still going on. I could loop this, but I'm not going to. I just wanted to give you a quick idea of all the precipitation that's occurred down here. And this is reflectivity, which is literally looking at rainfall or reflecting microwaves back from some kind of particles. Sometimes we can actually see bugs. When you see areas like this in here, there may be some ground impact from the radar and all. It can actually be interesting to watch sometimes because you can see things that may be important. Another area that Doppler radar does, it does velocity. Like if you hear a train and it goes by, it changes. Well, green is telling you velocity is towards the radar. Red and those warm colors like that would be away from the radar. So right now we're getting most of the wind directions are coming towards the radar in this area. Very light though, not a lot of wind down there right now, which is normal for summertime. One other thing is we now have dual pole radar. Dual pole radars are wonderful things. We're going to talk about those in a while. But by looking at them, we can see precipitation type. Oh yeah, radar is a beam that goes out from a radar that's going to continually rise. So while it starts out at a low level, eventually, the further out it gets, it's going to be higher and higher in the clouds. That's why you're seeing snow in this area, while rain in the lower areas. One of the nice things about dual pole, it can tell you where the rain snow is as far as height goes, which is very useful in a winter storm. But I wanted to know what the precipitation rate is right now. I can see there's some pretty good rainfall here by Lafayette, down through here, of almost an inch an hour. Here's some rainfall over an inch an hour. And if I was real interested and wanted to know maybe, how how much rain has fallen during the last day. This would be 24 hours of rainfall, and you can see, like down here in Mobile, Alabama and stuff, 2.5 inches of rain. Other areas over here, there's a real tiny little area as well. So this is another way we just use radar to try to estimate what is going on throughout the whole area. So I hope you get something through this. Yeah, and let me know if you have any questions.